Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody watching us from the future. So today is the final lecture. A bit tough right after Ascension Day for one last time, but today is a day of wrap up and celebration. So we don't have any new materials. So it's just to sit back and enjoy. We'll go through the material of the semester just on a high level to make sure that you see the big picture and how everything connects. I will also show you how this leads to large language models, which is another course at ETH that now you can take, or at least next year, which is kind of a follow-up historically of all of this. We'll have probably after the break, or it depends on the timing, right? But the announcement of the prize winners for the mystery game, where we have some very tasty sweets and chocolates for them. So some sort of award ceremony, and then we'll have the big quiz where you'll play against the TA. So at least George and maybe other TAs will have the courage to come and play against you. We have a great TA team. And then we'll finally give you the prizes. So the prizes for the big quiz game, it's this fresh from this morning. And of course, on Zoom, it's a bit tougher to transmit, but if the winner is in the lecture hall, then you can take it with you. And then we'll say goodbye. So let's start with the wrap-up of what we've done. And it's a very vast quantity of new knowledge that you have acquired throughout the semester. So now you look at this slide that I gave in the first week of the course with maybe a feeling of familiarity now, because you actually know what this all means and what there is behind. We looked at Boolean queries, which were the earliest systems. Then we looked at languages and saw that it's actually not so easy to bring the data in there and build the indices. We saw how to address tolerant retrieval, how to evaluate system, how to scale up building the index and building engines for larger collections. We saw how to compress the data, which can save you costs in terms of the resources you need to scale up. And then we moved over to advanced information retrieval, normally on the master's level, with vector space models, probabilistic information retrieval, and language models. And you saw that these two connect to these because that gives us the inverted document frequency, the justification for it, and that gives us the justification for the term frequencies. And this is why we have TF-IDFs in vector space models. So I like to say that this is actually a database lecture. Because we learn to store and query and efficiently query data with some query languages and some results that we get. And so in a way, this is the lecture for the fifth shape of data. So we have tables that you saw in database design and database modeling. But then we also have cubes, trees, graphs, which we'll see next semester in big data. And in this lecture, we tackled text. But one of the, I would say, new take-home messages that we got, especially in the last 10 or even in the last 5 years, is that, in fact, it's very efficient to view text as vectors. So it was already a bit visible through the vector space model that we could do that. But actually, with ChatGPT and large language models, it's validated that using vectors and linear algebra is the way to go to manipulate text and natural language. But before it went to that, historically, the first systems, information retrieval systems, didn't use vectors or that kind of advanced technologies. The first attempts just used Booleans, meaning that you would write a query with the terms that you would like the document to contain or not contain, with disjunction, conjunction. And we had a very simple query language with and or not that could be applied to some input collection, a set of documents, and then we would get a subset of the documents as the output of that query. No ranking, no particular order, we just give a few documents. And there were actually commercial products based on that, so especially appreciated in libraries, but also in lawyers' offices in order to research through texts. Then we saw that the concept of document might seem obvious in ancient times where we had codices and books that are the units, but this underwent digitalization, where now a document can be a web page, it can be a movie, it can be sound, it can be many, many different things, it can be a paper, and so on. So we have this abstraction of a document that is kind of what the collection is made of. We have a collection of documents. And then we have the terms, which is an abstraction on the words. The fact that when you look at language, the way humans speak a language verbally is basically based on some tokens that you can analyze on the level of syntax, on the level of the sounds, lexemes, phonemes, and so on. But in terms of information retrieval, we like to analyze them in terms of words. And again, we have the context of a term, which at first seems obvious because you just look at the spaces and what there is in between spaces. But actually, we saw it's not that simple. It's actually much more complicated than this. But from the level of abstraction, once you have done the work of tokenizing everything and getting the words out of them, then you get terms. And now we have a very abstract model where we have a collection of documents, and the documents contain or do not contain terms. We might be interested in the number of times they contain the terms, and we may or may not be interested in the order in which they contain the terms. But you see that mathematically, there is a lot of power in this, on this high-level way of looking at things with just collections, documents, and terms, with set of terms, bag of terms, list of terms, semantics. So we have this for the Boolean retrieval. And when we have this Boolean approach, we can use the set of words model, where either a term belongs or does not belong to a document. And it means that you can get a vector representation of any document as a vector of Booleans. So now you should be familiar with this. So the 1 says the vector is in there. The 0 says the term is in there if there's a 1. And if it's a 0, the term is not in the documents. You see here, that's very important to be aware of that. The structure of the vector is that there is one term per position. So we have an arbitrary order of terms, and every term corresponds to a position in the vector, and you can have a 1 or a 0, right? That's important because that's no longer the case with LLMs, that this is how the vectors are built. But with the old systems, every term corresponds to a position in the vector. Then we looked at several representations that we could use. One is the matrix representation, the incidence matrix, where you have the terms on the rows and the documents on the columns. And in fact, every column corresponds to this vector that I mentioned earlier. So this vector of Booleans corresponds to one column in here. That is the column representing these documents. All right. And so in order to execute queries, this is not efficient at all. There's a lot of zeros at many places, takes a lot of memory, takes a lot of time. And so in order to process the queries, we build what is called an index. An index is not specific to information retrieval. It's a generic concept in database systems, that it's an additional data structure that you add in addition to the collection. The collection would be the original data, and you add this data structure that takes some space, so it has a cost. It also has a cost in building it, that takes time to build. But once you have it, then you can process queries very efficiently based on this index. So you have one term, these are the yellow cells, these would be the terms. Then you have what you now know is the document frequency in the purple cells, the number of times, the number of documents that contain the term. And then you have the postings, the non-positional postings, which are the blue rectangles in there. And here, these are the document IDs. And the posting in here is a pair made of the document ID and the term that is right here, right? So this is called the standard inverted index. We saw that once we have this index, we can map Boolean queries to this index. For example, when you have an AND, you intersect the postings list. When you have an OR, you compute the union of the postings list. Since the posting lists are ordered, we can just do it in linear time. We just traverse them at the same time with pointers on every one of them, and then we can compute the union or the intersection. And not likewise, you can also efficiently execute the nodes. Then it's beautiful once you have the terms, but the hard part is to get the terms. How do you build the list of terms, and how do you map the documents to what contains and does not contain the term? And we spent an entire week just looking at it and seeing that it's complicated because of the complexity of human languages. So collecting documents, tokenizing, linguistic preprocessing, building the index, all of that is actually quite complicated, but we've looked into these things, and now we are equipped with a few tools that allow us to do all of this. Right? I made this slide a couple of years ago because it's very easy to get drowned in all the terminology, and so I wanted to clarify with this that there are kind of 6 concepts in there, depending on whether you refer to the concepts before it has been processed or after it has been processed. By processed, I mean this kind of process. You went through the language processing, you know what is the same term just conjugated in different tenses and so on. So all of this processing. And then, so that's the first dimension. The second dimension is it not tied to any document, or is it tied to a document, a specific document, and maybe even to a position in the documents? And that gives us 2 times 3 possibilities, right? And we have kind of names and terminology for all cases. So if it's raw and tied to a specific position, we call it a positional token. If it's tied to a document but without a position, it's a non-positional token. If it's still unprocessed but not tied to anything in particular, we can say word, we can say non-normalized type. And then if it's been processed with these things, so you haven't analyzed the language and so on, then you basically have positional postings, non-positional postings, and terms, right? Also normalized types. And the processed parts, that's what maps to the index, right? It's the terms that are the normalized types that corresponds to the yellow boxes in here. Right? So this is the processed part. The non-positional postings corresponds to the blue boxes in here, and the positional postings would correspond to the blue boxes, but if we turn the index into a positional index. We saw that some of the terms can completely be skipped because the posting list would be basically the entire collection, so it's very inefficient, and we can save us some space, which was particularly important in the 60s, 70s, 80s, so in the good old times where we didn't have that much computing space and power. Today, it's a bit less of a problem. So these are called the stop words. We just remove them completely. It's so frequent that they do not help. Another thing that we saw is as part of this processing of the tokens into the terms, we can use query expansion, query on both sides. So either we expand the index or we expand the query. And now, of course, now that we have LLMs, that looks a little bit prehistoric, right? The fact that we need to manually expand in there, because with an LLM, it just uses the embeddings, I will say a few words about that, to do these kind of things, right? But before we had LLMs and the luxury of the embeddings, this is how it was done. So very manually and programmatically that we did that. Also, mechanically and algorithmically, we have stemmers that allow you to kind of group the words in categories to get the terms. Again, this is kind of obsoleted by LLMs, which now do it with embeddings. But again, in the good old times, this is where we could relate the words together and find out that they relate to each other. We saw that if the postings lists are very sparse, we can have these skip pointers that allow you to directly jump to other places. So more precisely, it's when you want to compute the intersection of a very sparse postings list and another postings list that is not sparse. And because the other one is sparse, you might want to jump directly to postings. For example, imagine the other postings list has 1 and then it's followed by 11. The other postings list, then in this one, what you can see is that you can immediately see you can jump to 5 and jump to 9 and then go to 11. So you basically don't go through these if you know that the other postings list is directly there. So this is the idea of a skip pointer, which I am related to the generalization of that, which we also saw a couple of weeks later with, so that's one level, the skip pointer, but you can have even more levels. And this compares to walking, taking the bike, taking the train, taking the plane, you know, like in terms of transportation, if you consider that going through a postings list is transportation. And so the skip lists with more layers are used in vector databases. So when you look for the specific vectors and close to queries, these are actually very useful. And I'm just showing them next to each other because even though that was in the context of posting lists and that was in the context of the vector databases, vector space model, they are in fact the same idea from a theoretical computer science perspective, this idea of skipping. If you want to use fancy words, then these are basically singly or doubly linked lists with additional singly and doubly linked lists layers on top of each other. And then you can go up and down through this graph. Okay. Then we saw that we can improve the standard inverted index. That's why it's called standard, because we can modify it into less standard flavors. One of these is to use pairs of terms instead of terms on the left, or even 3 terms, 4 terms. And in that case, it's called a byword index, a 3-word index, a k-word index. And it has just a problem, is that it might return false positives. So it needs additional work to make sure that it doesn't return false positives. And you can reduce the false positives by just having a longer window. But the problem with longer windows is that it expands the space unit, right? And this is yet another problem that was solved by LLMs with the attention mechanism, right? But it's always important to see the historical perspective and the challenges that we've had in the past. This is the positional index, which is another way of handling the phrase queries, where this time, instead of the non-positional postings, we have positional postings. And that means that for every term in a document, it's not just set of words, it's lists of words, because we know all the positions in which the terms appear in the documents. So we know the order in which they appear. And that allows us to also, just like this one, process phrase queries. Right? Then the goal of an index is to process the query efficiently. But in order to process the query efficiently, you need to be able to look up the terms efficiently in the standard inverted index. And so that means that these yellow boxes that are on the left of the standard inverted index, they are organized in a structure, and that's again theoretical computer science, algorithms and data structures. And we have 2 main families of data structures that allow us to look up one of these yellow boxes, the terms. One is hash tables. It's instant, right? Just snap your fingers and then you know where the term is, but you cannot handle ranges. Or you can use tree structures, actually more precisely in the context of databases, B trees or B plus trees, which are a more modern version of the binary search trees, which would only have 2 children, but in B plus tree, you can have 10 children, 20 children. And the main reason for doing that, just not a binary search tree, but more children, is because of the hardware. The fact that you're reading from the disk and you want to make sure that whenever you read from the disk, you take a full block, right? See, if you just have a binary search tree, you would be reading much less. That's an inefficient use of the disk in terms of latency. So we have hash tables and we have B plus trees. These are the most common indexing structure. Of course, there's more structures than these. You also have in databases geographic index and so on and so on. There are even people who use machine learning indices. So instead of building a structure, they learn the structure to locate the terms. All right, but in the context of this course, hash tables and trees. A B plus tree looks like this. Again, as I said, it's a generalization of a binary search tree to more children. What's important in a B plus tree is that the terms and the postings lists are at the bottom, at the leaves of the tree. And everything that is not a leaf, that is up there, all of these nodes in here, here, all of these basically are only here for the lookup. They're only here to tell you go left, go right, and so on. But these are actually the terms on the standard inverted index that are associated with the postings lists. Okay. Then we saw that we can, in addition to Boolean queries, phrase queries, we can also execute wildcard queries. We saw that depending where the wildcard is, it can be easier or more difficult, right? It's easier if the wildcard is at the end. If the wildcard is at the beginning, you need to have another index mirrored. If the wildcard is in the middle, then you can use these tricks with the permuterm index where you add a $, and then you imagine that you rotate the words. So when it's at the end, it comes back at the beginning. And so you have all the rotations of plants, for example, in here. So then you can build a permuterm index. Another approach is to compute the k-grams. The k-grams is exactly the same idea as the k-word index, except that instead of words, you have letters. And so here you have, for example, the 3 grams of computer would be $CO, COM, OMP, and so on. Do not forget the $, at the beginning and at the end, because it identifies the start and the end of the word. And typically 2-3 k-grams are very popular. 1 gram or after that is either not very useful or not space efficient. Right? And that's also useful for the spell check. Whenever you want to correct a typo, then the k-grams are going to be helpful. Yet another way is the edit distance, which is the computation of the distance between two words, depending on the number of edit steps that you need to take between the two. And this is efficiently solved with dynamic programming, where you fill these 2D grids in here in order until you finally find the number at the top right, which is the edit distance between the two. Right, so also called the Levenstein algorithm. And as I mentioned, it's the same algorithm that gets you the diffs. When you use GitHub and you get a diff between two branches, it's the same algorithm, right? Instead of letters, you have lines, but it's exactly the same algorithm that gives you that. Yet another way to compute the proximity between words is the Jacquard coefficient, where you just compute the number of k-grams in the intersection divided by the number of k-grams in the union. Careful, it's not a distance, it's a coefficient, because the distance should be 0 when it's the same and higher if it's not the same, but here it's the opposite. It's 0 if it's completely disjoint and 1 if it's the same k-grams. You can turn it into a distance. People have done that. You need a bit of mathematical cooking to do that, but as presented here, it's just the Jacquard coefficients. And yet another way of looking for words that are close to yours is the Soundex algorithm that is based on how the words sound, specific to the English language, of course. And it consists in the encoding of the words based on the vowels. And so you have the dentals, the fricatives, that's all the fancy words that people specialized in phonology use to describe, like fricatives would be further, dental, DT, labial, L, and so, labial is m, these are the labial ones, yeah. All right, so this is the Soundex algorithm. And again, I mean, now with artificial intelligence and so on, we have much better ways to map the word to language, right? But historically, this is what came first. Then from a hardware perspective, we saw that whenever you want to make something fast, you have no other choice than to understand the hardware, the memory, the disk, the speed that it has, the cost that it has. So you have to spend some time on that. I'm not a hardware researcher, but I know that cache and RAM is much more expensive than disk and tapes. And I know that they're also much faster, but I also know that they are much smaller. Right? So you just need to have this hierarchy in mind in terms of the price, the speed, and the size. And to know that the first two need electricity to maintain the memory, but the other two do not. If you switch it off, the data is still preserved. Okay, and once you know that, then you can design algorithms for building the index much more efficiently. We saw that one trick that people used is to replace the terms with term IDs, just like you give document IDs to the documents, you give term IDs to the terms. And then these postings, which are pairs of term documents, they can be turned into term ID, document ID pairs, just during the construction of the index. And so we have this first generation of index construction called BSBI, where you have these batches of the collection, you partition the collection, and one partition at a time you create these term ID, document ID pairs, and then at the end, you merge them. Then there is a second generation algorithm that is an improvement over that one. So that's the first one. The second generation is this one called SPIMI, Single Pass In-Memory Indexing, that doesn't use the term ID trick. Instead, it directly built partial standard inverted indices for each batch, each partition of the collection, then merges them at the end. So it's great when that doesn't fit in memory, but it still fits on the disk, right? And if it does not fit on the disk either, then you go to MapReduce. MapReduce is the big data approach that's for indexing the entire internet, where you can use a cluster in a data center. Again, you have these pairs of term document ID. You don't need the term IDs in there because it's a data center. There's a lot of space. Yeah, so that is how you actually build Google or Bing or a search engine over the internet, MapReduce. Then the next problem that we saw, because now we deal with the internet, is that the internet changes every day. People edit their web pages, they add new content. And so if you want to maintain a search engine, it has to keep being updated to the latest version of the internet. And one of the tricks that we have for that is the logarithmic merging, is that you keep building a new smaller index with all the latest data, and then you keep merging it to lower levels. You can see it a bit like archaeology and fossils. You do it logarithmically, meaning that you merge every time with the small indices, and whenever you have a lot of indices of a certain size, you merge them and double the size every time. And this is the more you go to the right, the more it's the very old data that you will find. So that's a trick from an algorithmic complexity to handle the regular updates to the index. Then we saw, and that's a wisdom in general, not just for this course, that it's nice to be able to scale up and buy more machines and so on, but it costs a lot of money. And especially when you are a startup, you might not have that much money, and there is actually something much more efficient, is to try to compress and to make do with just one machine. There's a lot of startups that only need one machine for the first prototype. So for this, we looked a little bit at statistics to understand things. We saw that based on experiments, it's empirical experiments, Heap's law tells us if you keep growing the collection, you keep adding and adding more books to the collection, how does the number of terms, unique terms, grow? And we saw it's in the square root of the size of the collection. Very surprising, because we would think it's an asymptote, but actually no, it's the square root, keeps growing in the square root. And the second law associated with it is how the frequency, the collection frequency of the terms evolves. If I rank the terms by decreasing collection frequency, and I plot the collection frequency, then it's a hyperbole, 1 over n. So some constant divided of the rank. That's Zipf's law. Based on that, we found ways to compress. So now we can compress all the yellow boxes, which without the B+3, it's called the vocabulary. So we found ways to compress it. We also found ways to compress the postings, the blue boxes on the right. A naive approach was the variable byte encoding, which saves a bit of space, but an even better approach is the gamma encoding, which is elastic and adapts to the length. And remember that the trick, because the posting lists are an increasing sorted list of integers, we just need to encode the gaps in between. We don't need to encode the actual integers, just the gaps in between, which are always positive because it's a sorted list of integers. Just for those who are curious, I actually managed to extend this to encoding any decimal numbers in this way. It just uses the gamma encoding in the exponent. And you can encode all of the decimal numbers in such a way that you can compare the bits to tell if two numbers, which is the smaller one, which is the greater one, then you can do it on the bits. It's not part of the material of the lecture. I just wanted to mention it because that's cool, that you can actually also do that for decimal numbers of any. It's also elastic, any precision, any exponent. But again, this is not material. That's absolutely not part of the exam in any way. Then we went to a newer generation where we want to rank the results, which is a bit more familiar to people, because if you use Google or Bing or the newer search engines, you get the top 10, then you click next, you get the next 10 and so on. So we need to rank the documents and compute some scores. We saw that you can do that with a relational database, with the forms that you can fill on the metadata of the books. And this is actually how libraries used to do it. But it's actually a bit limited because you don't get to the full text of the books. It's just based on the metadata. But in fact, if you go to the full text and actually look at the content of the books, which we are interested in, then we saw that you can compute these scores based on the term frequencies and on the document frequencies, more exactly the inverted document frequencies. And so we can represent the documents as vectors with every term corresponding to one coordinate, and then you put the TF-IDF, which is the product of the term frequency and the inverted document frequency. And you can use a scalar product with the query, so document vector, query vector. You compute the scalar products, and you have a score. So it's this was an incredible insight to be able to see that you can use linear algebra to compute the scores. So it means that documents now are vectors of numbers, not just Booleans, vectors of numbers. So now you have a vector space. You have all of your documents that are just points or vectors in that vector space. So is the query. And so now the beauty is to locate the documents that are just the closest to the query, and these are your results. The closest they are, the higher they rank in the outputs, right? And the trick is to use the angle in between. So that's the scalar product. You can renormalize it too if you want, but that's the angle between the query and the vector. And since it's a scalar product, we love, computer scientists love it because a scalar product is just a big sum. And so the way you implement it is that you just accumulate that sum into buckets. Just you keep going through the postings and you add these xi, yi to the buckets. And then you have the scores that accumulate, and then you look at the highest ones, and these are your results. We saw that even though TF-IDF is the textbook approach, there's variations of that. You don't have to use TF-IDF. You can just use TF without IDF. You can use the log of the TF. You can use Booleans. So there's plenty of variations of that. And they have codes. You can encode them into 6 letters that basically tell you what convention you use for the queries and the documents. That's called SMART because SMART was the name of the system, the first systems that did that. And all of that gave birth to vector databases. And I think LLMs are also partly responsible for the hype on vector databases, but people realize that vectors now are so important technologically that we can build vector databases just like we have relational databases, graph databases. And so now this is a big deal. And so this is an example of extension to PostgreSQL where you create your vectors, you can insert them, and then in SQL, you can compute, so the L2 distance is just the Euclidean distance between 2 points. The L1 distance, also called Manhattan distance, is the similar but horizontally, vertically. Then you have the inner product, the scalar product between the two. And if you renormalize the inner product, you have the cosine distance. And the cosine distance is the one we used in the vector space model all the time. And that's great because all of that can be executed very, very efficiently with the vector databases. There's been a lot of research on that, on how to do that very efficiently. Yeah, that's the new buzz at the moment, the vector databases. But the insight that we could use vector spaces and documents as vectors of numbers is due to probabilistic information retrieval. So we did it at the end of the course, but in fact, historically, it came before. It's because people tried to have an approach of sorting the documents by the probability of relevance with the thought experiments with the elves in Antarctica. And doing that, you actually can derive a formula that in fact is the formula underlying the vector space model. The scalar products, the vectors, that all comes from this. The first insight came from this approach. And then we realized, so that gives you the IDF. The TFs come from the language models, but this is historically how we got the vector space model and the scalar products, by deriving from the probabilistic approach right here. Then we have language models. That was what we did last week, where you can look at generating data, just less advanced than LLMs. You just generate the terms in a document. You can compute the probability that terms are generated. We made a few assumptions, you know, this p-stop, 1 minus p-stop, the fact that we have a memory in the past of, in that case, just the last 2 documents that we remember. And that gives us the probability of generating documents. We saw that in the case you don't have any memory, then we want to group the documents into the bags for those that have exactly the same words, but in a different order. And that is important because counting how many there are, how many combinations there are, how many orders there are, allows us to write the formulas precisely to turn the list of words into the bag of words approach. And the difference between the two is these factors that you need to multiply it with. And finally, we derive an engine by having a thought experiment that you receive the query, you take a document at random, create a model, generate something, happen to find the query, and you ask yourself, okay, if that happened, then what's the most likely document I picked? And that gives us exactly a way to rank the documents based on this. And surprise, surprise, we get a scalar product, but this time with the term frequencies. So just like we got the IDFs from the probability approach here, we get the TF in here, and that is what gives rise to the TF IDFs in the vector space model. Right. All right. Then to evaluate system, you saw precision, recall, specificity. They have no more secrets for you. Just so you know, the fourth one, which is nobody uses that. I still haven't converged on the word, the cryptothesorion exhaustiveness. The only thing I'm saying here is that that doesn't exist, that is not standard, there is no name for it and no use for it. So it's only these 3 that are in fact the one that people actually use. And just for completeness, that would be the 4th one if people actually used it. Typically, we compute a harmonic mean between precision and recall, very often done in practice. For the ranking systems, we have these curves where you just click next, 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 and every time you update the precision and the recall, when you do that, you get a curve that goes like this. Another approach that comes from electronics is the receivers operating characteristics, ROC curve, that also gives you some idea of how the system is doing, right? So you want to have a curve in that case that is as close to this as possible, and in that case, as close to this as possible, if you have a good system. So now we've done all of that, and I would like to now do the transition to LLMs, the large language models. Who thinks they will take LLMs next year? It's in spring, every spring normally. Not yet? Okay. But in case you want, just as an appetizer, this is how ChatGPT and LLMs actually take it from there. The first difference is the scale. In the scale of the systems we saw in this semester, we had lower numbers, but the LLMs, that's why it's called large, go extreme in the scale. The number of tokens, the size of the collections that they work on, that's massive, like that's the entire internet. So that's the first difference between information retrieval and LLMs is the scale. Second difference, the tokenizing. In information retrieval, we kept it simple. We just use the spaces, even though language post-processing and so on still applies. But in LLMs, we don't care about the spaces anymore. An LLM can swallow anything. So basically, you just you can tokenize anything, and this uses information theoretical consideration and entropy to find the optimal way of doing that. But even if you trained an LLM that doesn't know Schweizerdeutsch, you can feed it with Schweizerdeutsch, it will be able to tokenize it and process it, right? So it's more powerful. But tokens now no longer correspond to words, that are separated by spaces. It's much more evolved. The second difference is that, the third difference is that in information retrieval, historically, when we had vectors, the coordinates of the vectors correspond to the terms, right? Maybe you have information that is the first number, retrieval that is the second number. And like this, you have 500,000 or 1 million coordinates on your vector. And every term is associated with a Boolean or a number. In LLMs, that's no longer the case. The vectors don't mean anything anymore, at least to a human. So we have vectors still. We still use the vector database. We still use the scalar products. We still use the proximity and so on. But it's no longer the case that every coordinate corresponds to a term. It corresponds to whatever, and that's abstract, right? So we just put the documents and the text in there, in that vector space, but in a way we don't really understand. But of course, that's a chicken and egg problem, because how can we create a vector space and put the documents in there in a way we don't understand? That's the magic of machine learning. So we actually learn it. We just create systems that have many weights, and that's also why it's large language models can have billions, trillions of weights. So this is we use neural networks, and the neural networks learn how to put the documents in there, how to place the points. This is something we learn based on these systems. And it's learned in such a way that it works, right? So under the constraint that it satisfies all our goals, it learns how to place the points in there, right? So on the left, no machine learning. We can do it programmatically. On the right, we use machine learning to put the points in the vector space in a way that actually doesn't make sense to us humans, but that happens to understand or create some semantic understanding of the data. Another difference is attention. We saw in the language models that we have this Markov chain where we only look at the 2 or 3 or 4 preceding terms, right? But in LLMs, we no longer do that. We look at everything, even in the future, not just in the past, also in the future. And so we have this attention mechanism that you might, who saw the paper, Attention is All You Need, right? That one became very famous. This is what it's about. So you no longer just look at the past few terms, you look at absolutely everything, right? So the entire, you relate the terms with everything that is in there. For example, if you have a pronoun like I or you or he or she, then you just relate it to some other place where you might have the person or the noun that it refers to. That's part of the attention mechanism. Of course, when you generate content, there's a trick that you just remove that, because of course you cannot know the future. So when you generate, you just have a mask in here that hides that, and then you just do it based on the past, right? So this is attention. And finally, all of that means that instead of just searching and ranking, now we can use it. I mean, probably everybody uses it. Now we can translate, even in real time, we can write, get generative AI to write text, to summarize, and so on. And semantic search, also very useful. When you search for a certain thing on the internet, it can actually, in quotes, understand what you're looking for in the sense of the expansion I said earlier, lift, elevator, and so on. So now that is done almost natively, this kind of semantic search. All right. And so this is an appetizer for this course, which is taught by Ryan Cottrell, Mrinmaya Sachan, and Florian Tramer. And normally it's every year. So if you want to take it from there and study large language models, then you can do it in your master's next year. So now we are almost at the break. Do we already have TAs? Not yet, only Georges. So what we will do, maybe they come after the break. But that means, Georges, that you will get all the applause, because now we are going to give a big applause to the TA team. And so, Georges, you receive here all the appreciation and the applause. So thanks a lot for the amazing work this semester. The TA team is still working very hard on the preparation of the exam, which will be in August. Speaking of the exam, everything here is that we covered in the lecture is material, except when I said it's not. So the slides, the recordings, the textbook, the theoretical exercises, the practical exercises, the clicker questions. You really should read the textbook if you haven't done so. It's more or less the same thing as in the lecture, but gives you another perspective by other people, and so it's good to consolidate everything. Since it's exactly 11, maybe we'll take the break, and right after the break, I'll explain, the exam, Moodle, what to expect. Then we'll give the prizes to the lucky winners. Well, not lucky, competent winners of the mystery game, and then we'll proceed to the quiz game. Right. So I'll see you in 15 minutes.